That's why I'm really struggling as much as I am. So any prayers for our school, for our students, the staff, just the students' families, very, very much appreciated. Thank you.
Yeah, what school do you teach at?
Alchesay High School in White River.
In White River. Okay.
Yeah.
Okay. All right. Okay, guys. Geez, that's terrible. Sorry about that. How many students are at your school? How many are seniors at your school?
How many are seniors at our school? We probably have about 200.
So it's a pretty small group as it is, and probably a pretty, let's say, isolated but tight group, right?
Okay. Yes. Yeah.
Gosh, that's terrible. That's just awful. Okay. Good. That's some news to start on. Okay, so any questions you have for me? So we've done some of this before. In the 509 class, I didn't grade much. To some extent, that'll be true for part of this class, like the homeworks. I gave you an idea of what I was going to try to do grading. This class is now pretty small, so probably I can do that, like look at a couple of problems. Of course, I try to look at the DQs, right? So you get some feedback there, right? Not so much grading. I mean, it's a little bit different than you would get on an exam, for example. The difference in this class is about 50% of the grade is on the 2 exams, right? And those will be graded, right? Those will be thoroughly graded. And I'm going to try to do part of that in class, either do like do the true false stuff, maybe not the justifications, but just the true false part in class. Or maybe meet with people. I haven't quite decided yet. Just like have you all here, all your cameras on, do the true false, something like that. I mean, it's just one of these things, it would be nice to have some exams that were, I want to say monitored. It's the wrong word, but like where we're sort of watching you, right, to make sure you're not just. Anyway, in the take-home exam is usually you'll have several days. And the problems, because you're taking them home, are a little bit longer and harder, right? And I don't remember in 509, I probably didn't use AI too much, but if you looked at this class some, you'll see that I'm using it quite a bit for various things. It's kind of fun to play with, and I'm giving you some AI tutors to try out, and I would like to hear some feedback if you're actually using them. One person gave me a little bit of feedback on those. The feedback being sort of that they're maybe too kind in what they say to you, right? And so maybe they're not giving you enough information back as I would hope. And of course, I can go in there and sort of tell them to be harsher, right? But it is hard to get them to do exactly what you want them to do. But each one that I give you is sort of trained on the chapters and the current topic, and it's got my solutions, and it's got the official book solutions, and so it's got your problems and also the problems you're doing and all that stuff, right? So it should be pretty good at answering your questions, right? And you should be able to, like, if you're typing stuff up, you should be able to just post your stuff in there and ask it to, I don't want to say grade it, but give you feedback. And if it's too nice, you can ask it yourself to be able, like, what do I really need to work on? That sort of stuff. There's going to be a lot of proofs in the class, and so the only real way to deal with doing proofs is to read proofs and do proofs, right? I mean, what I would really suggest as you're reading your text, when you get some definitions, right? Then you got a theorem, right? I would suggest trying to prove the theorem yourself. See where you get stuck, then like read the proof, right? See, what are, is what you're doing, what's the book is doing at the same time, sort of get some self-feedback like that, right? And then in the homework solutions I give you, make sure you're actually taking those things and comparing them to your work, right? I can tell when I give the exams, because when I do give the exams, I tend to give you the ability to improve your score on the exam so what I'll do is I'll take up your exams. I usually give you the solutions after that and say you can do corrections for up to 50% of the points back, right? That's a lot, right? That's a lot of points back you can do. But what becomes clear to me is that the people who didn't know what they were doing in the exam in the first place also really don't have a clue how to read my solutions, right? They really are just so lost that you don't know how to do that either, right? So it's really, really important to read the solutions, understand what's there, right? Keep in mind that there's often many, many ways to do the same thing, right? So if I do something different from what you do, that's not terribly surprising, right? If you think I'm doing something wrong, you should let me know, right? If you think you're doing something wrong and you have a question, you should let me know, right? So all the usual sorts of things there. Good. All right. So now you have, so I'll share a screen here. Actually, let me just real quickly grab a snapshot of everybody here so I can do that. I think maybe one person is missing that I should expect to see here. And let me save this. Sorry, let me do this real quick. Oops. If you, by the way, have like an image of yourself that you would like to share that's small, you know, like I may use these for the meantime, because I'm really bad at facial recognition, right? It's just not one of my things. I mean, I look at some of you and I say, oh, I remember you from before, right? But actually your names just, you know, sort of flew by me, right? Now I'll interact with you a lot more this semester. So hopefully I'll get some of that. I'm just terrible with names and things. Okay. So up front, but if you have a picture that you'd like me to like put into my roster so that maybe I could look at you sometimes and say, that's Pringle, right? Or something, right? Then that might be a useful thing. Otherwise, I may just cut out the little pictures I'm getting here. Some of you I'm just getting like your heads, and then it's mainly like cut off by the words and stuff. Okay, anyway, we are going to start. So unfortunately, this class starts pretty darn fast, right? There's actually 4 chapters, right? Some of which is actually on the topic of group theory. A good amount of it is on background material, right? Of which a lot of it is actually very important, even for doing group theory. And it'll become even more important when we get into the ring theory later on, okay? So what we're doing in this class to some extent is studying algebraic structures, which generalize things that you know about, right? So you know how to do algebra with numbers, you know how to do algebra with, you know, just the integers, maybe just the whole numbers, with the rationals, right? You know the differences, you know what I is, you know the complex numbers. So you have all these ideas of number systems, right? In some sense, when you did linear algebra, right? That's another algebraic system, and you can think of matrices as being generalizations of numbers too, right? So, you know, there's not a bad way to think, and in fact, being a generalization of complex numbers is a pretty good thing to think about with matrices, right? But we're going to see that even much more in this class, right? And so, and not only numbers, but you know, we'll have algebras of functions and, you know, all sorts of things, right? So there's lots and lots of algebra in math, and this class will occasionally also touch on some geometry and things like that. So, you know, just keep an eye on it, you know, have questions when you will. Some of you said you were really interested in doing some real life applied things, right? Turns out that most things like that are actually really hard to do. I mean, it sort of involves a lot of stuff and a lot of background and those, you know, and I'm not an expert in a lot of it, right? So if you find something you're really interested in, first of all, keep in mind you do have a project, so keep that in mind for something you might do as your project. And secondly, you know, ask me about it, right? But don't expect me to know what you're talking about immediately. You know, you can give me some heads up and let me look at it and think about it some. Okay, I mean, I don't find all this stuff completely trivial. When I sit down and work your homework and stuff, you know, it takes me a while, right? Okay, so let me just close this stuff. I'm going to share this. If I start breaking up, let me know. So I have changed my internet thing here, and it does have a pretty slow upload speed, so it wouldn't surprise me if there starts to be some problems. And I think maybe we had some of those problems before, so let's see what happens. Maybe Jordan, you had a question? You're muted right now.
Yep, gotcha. No, not so much a question, more of a like an observation, but the book kind of opens up talking about modular arithmetic, and it talks about like the UPC codes and stuff.
Yep.
And that's actually like I was lesson planning this week on Sunday, and literally that's the exact topic I'm doing with my seniors. So I just thought it was a big coincidence that I learned about it prior to lesson planning. The only difference is it doesn't really get into the modular part. It just talks about how if it's correct, then it ends with a 0, which is essentially if it's mod whatever number, then it won't have a remainder. So I just thought it was interesting.
Okay. And what class is that for? Is it like
it's called Advanced Quantitative Reasoning. So it's more like a practical math class where we talk about like, real world things like tires and aspect ratios and things of that nature. So
okay, awesome, cool. Good. And then I thought I saw someone else's hand pop up. Caitlin.
Do you by chance know where we could find a PDF version of the textbook? Because I've been going through the textbook and there are a couple of formatting issues.
So I can't officially send you one, but if you unofficially send me an email, I might be able to find one for you. Because I agree, those books that you have aren't the best at formatting things, and sometimes it can cause a lot of trouble. So I'm aware of that. We're aware of that. Like that's one of the things we're asking to change is to get you guys PDF copies of these books instead of using that that reader. Also, you can flip through them much easier and stuff like that, right? Write on them and all that sort of stuff. Okay, so it is a thing we know about. Okay, let me share this screen here. This is where hopefully it won't slow down on us. And then I'm gonna have to move some stuff around. Let's see, do that. Okay, there we go. And I think I've got all that. Okay, so here's sort of a, the mini lecture that I guess maybe 2 times teaching this class before, this started off being a mini lecture with no videos. Now it's a mini lecture full of videos, right? And so I'm sort of assuming that you've watched these videos or some of these videos or will watch these videos or something like that, right? And what usually happens, because there's so much material, is I make it through a little tiny portion of this, right? Because each video here is like 30 minutes long, right? There's a bunch of them, and we only have 2 hours, right? So it's not a lot of time. So what I'm going to do is not directly talk about these. I'm going to sort of go in the same order. But I'm going to use something a little bit less complete, right? So it means I'm leaving out some stuff. Sorry, keep having to hide things and move things around. And okay, let me do that. Okay, and let's see. And this is kind of cute. I had your TA, the AI TA, make me an idea of like how to schedule out timing, right? And we're already messed it up because we're already like 16 minutes in, and I was supposed to be through with this before 10 minutes. But so anyway, it gives me sort of a shorter way of doing things. But and it does ask a good question. It's sort of interesting what it comes up with. So I'm just curious. Not everyone has to answer this, but like, what do you think of when you think of like what a structured set is, or maybe what a algebraic structure is? And you have some examples already. And of course you've been reading. So anyone want to say anything about that? You can put it in the chat too, if I can figure out how to look at the chat at the same time. Like, what does it mean for a set to have structure? So, so I'm assuming everybody's seeing the chat too, right? So Caitlin, it looks like what you're saying is just sort of a set, right? So that's a set of, and I'm assuming like different objects, not just like. I mean, it's a good point, right? So like the set of number, right? say this was actually your set, right? What is, and in terms of a set, what is that? Let's say these are literally the same thing, right? So in terms of a set, what would this set be?
Just the one number, if they're
It
all
would-
the same thing.
Yeah, right. So it would be just like that thing there, right? So that's the thing about sets, right? Sets don't have, I mean, they can have repetition when you write them, right? But kind of as an actual mathematical object, they don't have repetition, right? So that's an important thing. Now, what if I put like number? So now what I might call this sort of structured thing a what? Instead of a set, I might call that a
Sequence.
sequence, a list, something like that, right? And so here, you know, let's put two different things in there so they look a little bit different, right? But that sequence there would be different, right, than this sequence here, right? Because the order matters now, right? So it is a thing, you know, I mean, and you do want to use the right notation. I mean, when you're doing sets, you want that set notation in there, right? When you're doing, and this will come up a lot, right? When we're doing sequences, we want to write things as sequences, right? And then sometimes you put like also, these are not ordered pairs, but like 1, 2, 3, you know, a sequence might, and we'll use this sort of notation a lot, right? Say, I don't know, in, right? Something like that, right? So sometimes you put these like little ordered in tuple type things around them, right? Okay. What else in terms of structure? Let me see. It feels like properties. So some sort of closure, right? And so that's good with the idea of like vector spaces, groups, right? So you have some sort of operation that they should be closed under. Continuous functions, maybe closed under composition, right? Things like that. Or maybe even like products of like if you have a real valued function, right? You could take the product of two real value functions and you could add them, right? And in fact, you get a vector space, right? So that you should know that from 512. So it's set with a binary operation. Yep. Crystal, you wrote just number. I'm not sure. You mean like the number systems?
I think that was in response to your
replying
question
to-
of the
replying to your
repeating
question about
numbers.
the
Okay. Yeah, some sort of grouping. Good. Okay, that'll come up. That'll be something we look at in a bit. Okay, and now this looks like maybe a helped. This looks like an AI assisted answer. Am I right? Who's Deanna, Dina, right? That was yeah. Okay, so this makes a good point, right? Since I use AI a lot, I know how to recognize AI answers, right? And I'm happy for you to use them to learn, right? But like when you do your exams and homework and stuff like that, make sure you don't just cut and paste from some other source, right? Make sure you write, even if you just go through the effort of writing out what the AI said, you're still going to learn something, right? But I'm really interested in what you're learning, right? I'm not really interested in you giving me right answers. I have the right answers, right? So that I'm not interested in, right? I'm interested to see what you're learning. Of course, in a thing like this is fine, right? So this is certainly fine. Good. All right. So anyway, it's the sort of, we're going to talk about abstractions, right? So that's sort of the thing. Now, a little bit on chapter 0. Chapter 0 has a lot of stuff, okay? So I want to just focus on a little bit of it. We have a little bit. We've got some set theory notation here. You know what functions are. You know, when you're talking about functions going from a set to a set, right? So not necessarily on the reals, but you know, some function. So the notation is like this, right? Like that. These would be sets, right? Those two things, well, those things up there, X and Y would be sets, right? This would be a function. What property, and if I were to draw this, like here's X, I mean, none of this should be new, right? And I have an X over here and it gets mapped to something over here, right? And so this might be called f of X, right? And so we might indicate F like that, right? And here's one important thing. When we talk about functions, this set X is the domain. Everything over here needs to map to something over there. Okay, and it's not the case, and so this would be the domain. Now, is this thing over here necessarily the range? Or what should the range be?
It's the codomain, right?
So not quite, right? So codomain is a nice word. So this Y here is what I would call the codomain. What would the range be?
The image?
Just the image, right? So, I mean, so unlike the domain, right, it might be that just some subset of this actually gets hit by something, right? And so the range is whatever gets hit. And we do, so another way of writing that would just be to write f of x as a set. You know, everything that comes from something in X, right? And image is another good word, right? So, and we'll use that in this class, right? So image of F, right, would be another thing. And I often will write range of F, right? So there's really three sets, right? There's a domain, there's an image, and there's a codomain. Okay, and it's sort of good to keep those in mind. If I just give you the function without telling you exactly what the codomain is, and all you know is the points that map from and to, you don't actually know the whole function, right? So, and notice that this is different than what you might do in a high school class. Like we tend in calculus to write something like f of x to the square root of x, right? And we tend to discuss this as if it's a function from reals to reals, right? And that's not really the case, right? This is really a function from this half open interval, right, to the reals as a codomain, right? And then the range itself is actually also this same interval, right? This would be sitting inside of that thing. And we could view the function like that, but without telling you what exactly the codomain is, you don't know which one I really mean, right? Could be either one of those two things. Okay, so these are just words, right? But an awful lot of what you do in math is definitions in words, right? So that's part of it. I expect you to, be able to take unions, intersections, cross products, right, of sets, ordered in tuples, right, all that sort of stuff. So make sure you look at that, and if you have any questions, ask. And I guess I'll stop for a second and say, do you have any questions on that stuff? Okay, good.
Dr. K, is that last image, so that says f of x, image of f, and image of y, or image of t? What does that last image say?
There's image of f right here, because my function here is f, right?
And then up under it, what did you write?
So this is the range of f, so everything is f, right?
Oh, that's an f, okay. So you wrote image of f twice?
No, this is range, sorry.
Oh, okay.
I tend to use RNG for range. So these are like three different ways of writing exactly the same thing.
Understood. I was just asking for clarity as I take notes.
Yeah.
Thank you.
Mm-hmm. Yeah. Okay, so let's see. So okay, let me say a little bit about modular arithmetic and just sort of make sure that we're in sync with some of this stuff. So let's consider modular arithmetic first, and then I want to sort of back up and think about what a equivalence relation is and what equivalence classes are and that sort of stuff, just so we make sure we get all this stuff kind of straight. So first of all, we have this nice theorem. So here we're working in Z. This will be a set which we work in a lot in this course. It's going to be like when we get to rings, we're going to look for rings that behave a lot like the integers, right? So the integers have a lot of special properties, right? And we're going to want to be generalizing those special properties to other rings. And so, for example, in linear algebra, you looked at things like a field of polynomials, right? Over the field, right? This was a vector space. This would be an infinite dimensional vector space. And as long as that F there's a field, this actually behaves a lot like Z, right? So this is going to be the sort of stuff we're looking at, the second half of the class when we get into rings. So one theorem you have here, and we'll have the same theorem for this guy here, is we know that if I have any two things in here, M, And let me take, just to be maybe a little bit careful, let me take m to be not, well, okay, m not equal to 0. Actually, since it never matters, let me take m to be greater than 2, greater than or equal to 2. Okay, I'm just going to say m greater than or equal to 2. All right. Okay, and then we're going to, then we know, right, for any n and, I don't know, something else, k, right? For any n and k and z, right? So everything in z here, m greater than or equal to 2, there is a unique, let's call it q and r, such that n equals m n, no, q n. Sorry, I got my, I used a different letter than I meant to use up there, so I'm trying to stick with it. Qm plus R, right? So that's what I want to say. All right, so this means there's a unique, right, QR such that this happens. And it actually, yeah, this is a good question. This is like a little mini test. Do I have this quite right? Like, is this actually correct? Like, suppose I gave you a true false question. I said, is this correct, right? Is this correct?
I would say yes.
So let's take like, let's like 10 and let's say n equals 10, right? Let's take m equals 3, right? So what's sort of the obvious thing here? So 10 is equal to 3 times 3 plus 1, right? So that looks good, right? But isn't 10 also equal to like 3 times 4 minus 2? Right, that's also true, right? So yeah, so yeah, so that's not quite right. What's the extra thing I need to add here?
Do you have to say what R belongs to? Like, is that
R
the right?
has to be greater than 0 and less than n minus 1.
Right.
So R needs to be greater than or equal to 0 and less than n or less than or equal to n minus 1, right? And in terms of saying what it needs to belong to, right? If you're ahead of the game, you might say it has to belong to Zn, right? So that would be a way of saying that, right? That's another little good piece of notation to get out of it.
I guess my wondering is because that's the part of the formula that you transpose back to when you're doing modular mathematics, right?
Yep, exactly. Yep.
Okay.
Yep. So yeah, so it's very important that this R is in this interval here, right? Otherwise, it's not unique, right? So that's the thing. And just to make sure we're in agreement about that, Zn, right, is the set 0 through n minus 1. Just as a set, right? That's what it is. Okay. And it is the set of remainders, right? This R here is called the remainder, right? And so this is the set of remainders when dividing by n. And I'm sorry, I keep going back and forth between m and n here. So maybe I should call this Zm, and let me call this m, just to be consistent there. Okay. What is the relation that we have? So our, like, so, oh yeah, by the way, what is this theorem called? It's got some sort of name, right?
It's modular something. It has to do with the modular.
Division algorithm?
It's called the division algorithm usually, right? So this is the Euclid's division algorithm, right?
Yeah.
There's a strength. Sorry, go ahead.
No, I was saying it comes right after you talk about order. That was the next lesson after order.
Yeah, there's a strengthening of this that's called Bezo's theorem that we're also going to need. So I'll say something about that in a minute. And actually, I think this is a good example to prove using induction. So we're going to maybe look at that just a little bit, right? What is the relation? Like, when do I know? Like when I have m. So I have this unique. Sorry, let me back up a little bit. So I have this unique remainder, right? Let's go back to talking about functions. So I've got n, I've got my m, right? I've got a unique q and m plus r, right? So what are unique? That q is unique, right? and that R is unique, right? So those two things are unique, okay? So this Q is often called what?
Quotient.
So it's the quotient, the integer quotient, right? And I think it's always the same as this, right? I got to think a little bit with negative numbers, but I think this is true. So this is like the greatest integer less than or equal to n over m, right? So that's one way of writing that, okay? Maybe another notation. Do you guys have this notation? Maybe sometimes you see this notation. Right? This is kind of greatest integer function, right? Okay. What is the R called? Because it's unique, right? Because this Q and R are unique, right? You know, we have this kind of function. This is like a function of these two variables, right? In M, right? So this function is the greatest integer function. Quotient, right? What is the R called? What's the notation we use for that?
The remainder.
So it's the remainder, and what's the notation? We're doing modular arithmetic, right? So what's the notation here for this?
Is it n mod n or
So
n
here it'd
mod-
be n
M.
mod m. Yeah.
Oh, yeah.
Okay, so this is the remainder when dividing n by m, right? So if you want to put these two things together, it's always the case that n is equal to n over m, which is the quotient, times m. Now m can be n can be negative, right? And then plus m I'm taking to be positive, plus n mod m, right? So you can always break an integer up like that, right? Given an n and an m, right? So this is a function and this is a function. We won't do much with this function, but we're going to do an awful lot with that function, right? So so what happens when you have these divisors? Like what happens to z? Let's say we're looking at mod 2. Let's do like mod 3 just for the fun of it.
Sound like a rubber band.
2, 3, 4, 5, you know, -1. So
Your screen has
so
frozen.
which things have? Oh, my screen's frozen.
Your screen is frozen and you sounded like a rubber band.
Oh my God! No. Still?
Yep, all we see is you erasing something. Now it's caught up.
Okay. Do I still sound like a rubber band?
No,
No,
sir.
you sound better.
Okay. Let me know as soon as that happens. And I mean, it's possible I might need to turn off the camera too to see if that helps. What are the elements here that have remainder 0? So clearly 0 has remainder 0. What else? Mod 3, right? That's our
Negative
thing I'm
3
modding.
and
Negative
3.
-3,
-3, 3, 6,
9.
etc. Right? So
12.
anything of the form 3 times k, right? Where k is an integer,
Yes.
right? So we might say here that the equivalence class of 0, all the things that have remainder 0, right, is exactly the things that look like 3z, right? And so what this notation means is I take the number 3 and I multiply it by anything in z, right? And so that gives me the whole set of things that are of the form 3 times k for some k, right? Okay, so this is a common, I mean, we're going to use this kind of notation a lot. So if I have an element of a set and I have a set and we have some sort of operation like this, right? When I just do element times set, I will mean the set of all A, B, where B is an element of B.
Dr.
Right.
K, what's the I think I missed it. The bar above the 0, would you say that notation means?
so I'm calling this the class, right? So it's the set of all things that have remainder 0, right? So the bar at the moment is just saying I'm looking at the whole set, not just the number 0, right? But the whole set of integers that have the remainder 0.
Okay.
Right?
Dr. K, where you
Yep.
use the bar as such that in the textbook, it says that means AB divides B element of B. So how would we know when to distinct, well, I mean, obviously right now I can distinguish the difference, but are we gonna ever use the bar as divides?
Oh, I see. Yeah, we use it for both. Yep. I mean, yeah, when you're doing sets, this means such that.
Right.
When I'm doing something like 2 divides 6, that means divides, right? Or
Yes.
2 does not divide 3, right? That is not
Yes.
divides, right? Yep. So we use both. You certainly do.
Okay.
There's a lot of, yeah, there's only so much notation, a lot of things to say, right? So if I just, this is like also more notation, right? So if I have 2 sets and I have an operation, right? I'm multiplying 2 sets like this. This means that I'm looking at this little A, B, such that A is in A and B is in B. Okay. Hopefully this notation makes sense.
Yes.
If I'm doing like A times B plus C, right? So where this is a set, right? And the other things are elements, right? Then I mean, these are the set of all things A, B plus C, where B is in B. All right. So do you see the pattern? I mean, you can do this for all sorts of stuff, right? Does it make sense?
Yes.
Okay. So what is so going back to this, so 0 bar, that's what I'm denoting here as, so it's literally this set, right? It starts at 0, it's got 3, it's got -3, it's got -6, it's got 6, and it goes on that way, right? And so this is 3 times Z, right? What is another class of remainders, right? So these are all the remainders 0. So remember the modulus here is 3. So what's another remainder I could have? So I could have 2.
2 and 1.
2 and 1, right? So let me start with 1 because it's the next obvious one, right? So 1. So this is going to be, right, 1. And then I add 1 to everything, right? So 4, 7. Now when I add 1 here, I got -2, -5, et cetera, like that, right? And so this could be 3Z plus 1. Right?
Right.
And it would give me that. And then same thing, 2 bar, right, would be 3Z plus 2, right? Now here's an interesting question. Suppose I take a couple of things in 1 bar, right? So like I take 4 and 7. Well, I take 1 and 7 and 4. Sorry, take 1 and 7 and 4. Let me try that again. All right. What can I say about these classes? 3Z plus 1, 3Z plus 4, 3Z plus 7.
They're the same, because if you subtract, 3, you can take a set of 3 out of 4, and you can take 2 sets of 3 out of the 7, so they all simplify to 3Z plus 1.
Yeah, good, right. I mean, if I start with 0 and I add 1, right, then I'm sort of getting this set. If I start with 0 and add 4, well, if I just go back 1 and sort of move forward, that many, right, I get exactly the same set, right? And you're getting at sort of a relational way of doing the same thing, right? Yes. So the point here is we kind of have this algebra, right, where if I called this thing here, maybe I call this thing 7 bar, right? Because that's all the things where I started with 0 and added 7, right? You sort of have this idea that 1 bar is equal to 7 bar, right? So far, I haven't really talked about any division, right? I'm just sort of playing with these sets of numbers, right? And so the point is we can sort of build the modular arithmetic in 2 different ways here. One, thinking of them as sets of numbers like this, and the other is thinking about this division relationship. Okay, and these are really closely related. So what's a different way? And of course, we tend to just look at the, this is a complete, I mean, that's all the classes there are, right? So this is another way of saying what Z3 is, right? But here, instead of just sort of defining an algebra on the number 0, 1, 2, right? I'm literally looking at the classes in here, right? I'm defining how do you add classes? Like what is 2 bar plus 2 bar here, right? So this would be like 3z plus 2 plus 3z plus 4, sorry, plus 2, right? And that's the same as 3z plus 4, right? But what was 3z plus 4? Well, it's the same as 3z plus 1, right? So this is really just, yes, this is really 1 bar, right? So this is like showing that 2 bar plus 2 bar equals 1 bar, right?
That's so beautiful.
And I haven't done any division yet, right? I'm just sort of playing with these blobs of numbers, right? So that's kind of the point. This is sort of the difference between thinking about equivalence classes and equivalence relations, right? So what I want to do now is sort of turn to the corresponding relational view, okay? And so when we're doing modular arithmetic, how do I say, so remember we use this kind of notation like 4 mod 3 equals 1, right? So this is like a function that gives me back the remainder, right? So here's a relation for equals 1 mod 3. So now here's a case where you have to be a little bit careful about what's being said here, right? So you might see an extra set of parentheses there. And in my notes, I tend to just write it like that, right? So you have to think about, am I talking about the relation or am I talking about the function, the modular function, right? And so what does it mean to say, whoops, to say A equals is equivalent to B mod M?
That's saying that M divides A minus B.
So there's a lot of different ways. So one thing you could say is it means that A bar equals B bar in the notation we were just talking about, right? So that's one thing you could say. Another thing you could say is you could say that A mod M as a function, whoops, is equal to B mod M as a function.
Okay, never mind. That's what I was
Right.
going to bring out. I knew the second part. I didn't So wouldn't that 4 be 4 mod 3 and is equal to 1 mod 3? Is that what the congruent symbol means? That congruency means that the 4 and the 1 are congruent?
Yeah. So I mean, yeah, but this, yeah. So literally, this is the notation for congruent, right? Mod n. This can also sometimes be written like this: A equals MB. Sometimes that's really useful when you have a whole series of equalities you want to express, right? So when you're doing algebra and you sort of have a sequence of equalities you're trying to work through, it's useful to think of this like an equal sign, except it's mod m, right? So you have to think about it like that. The other equivalent here is what, I forget who said this, but you would say that M divides A minus B. That's another way to check.
That's what I said.
Right. So there are, all three of these things are the same. In fact, all four, right? I mean, this notation here, maybe 5, right? I mean, there's a notation here, there's a notation here, right? And then all 5 of these things are sort of saying the same thing, right? Okay. And depending on what you're doing, sometimes one or the other of these is the easiest to use, right? So we'll see that a lot as we go. I guess the one that generalizes the most, and we'll see it a lot later on, is this one, right? Because yeah, I think in linear algebra you probably did quotient vector spaces. Did you do that? Okay.
Yes.
So here we will do quotient. So I could look at Z quotiented by 3Z, right? And that's actually going to give me this Z3, you know, our modular arithmetic. And the elements of this thing here will be exactly the things 0 plus 3Z, right? 1 plus 3Z, and 2 plus 3Z. Right? And if you think back to like if you did a quotient vector space, you're doing exactly the same thing, right? You've got some subspace, you've got a vector space, right? And the quotient vector space are going to be the set of all things of the form V plus U, where that's set, right, there for V in V, right? So this is a very, and here I'm saying Z mod Z3, 3Z. So this is the set of Z plus 3Z. Maybe I shouldn't call this Z. Let me say N plus 3Z, where N is in Z, right? So it's really kind of the same construction. I mean, it's actually literally exactly the same construction. Right. So this kind of constructing new things from old things, right, is something we'll see.
That's Z such that 3 for every equal the set that you have. Is that an upside down A right there?
This says,
no.
So this says Z mod 3Z.
Oh, that's a Z. Okay, my bad.
Is equal to N plus, no, it's good. Keep me writing slow, which is better, right? For N element of Z, right? That's what it should say. Good, so we have this relation, which I might call equivalence of M, right? Just to use this notation for a second. And it is a special kind of relation. What kind of relation is this, right? So again, I'm just sort of checking your reading.
Congruent.
So it is a congruence relation. So if I'm just thinking about the set theory part, then it's also an equivalence relation, right? And so what are the rules of an equivalence relation? I know that A equals, MB implies what? Actually, I'll just write the rules down and have you fill them out. B equals MC implies something. And there's one more that's just kind of for free. So I'm saying fill in these question marks. And there's one more that's just like a question mark there. So if A equals mod MB, then what do I know about B equals M mod A? Or B is congruent to A mod. If A is congruent to B mod M, right? Do I also know that B is congruent to A mod M?
So M divides A and B. Is that what you're saying?
Yeah. So I mean, yeah. So one way of saying that is that if M divides, let's say we define this literally as A minus B here, right? Then it means that M divides B minus A, right? So the order doesn't matter there, right? So that's the point, right? So if A is related to B, then B is also related to A, right? And so what is this property called?
Transitive, reflective.
It's not transitive, it's
commutative or associative.
Commutative. No. So these are good. Yeah. Okay. So commutative, associative, these have to do with operations, right? There's no operation here. We have a relationship, right? We've got a relation, right? So this is called symmetric.
I knew that. That was on the tip of my tongue.
What is going to go in this little question mark here? Now, someone actually did give the answer already. So A is related to B is related to C. Then what do I know?
A is related to C.
A is related to C.
By the transitive property.
That's transitive.
Said that, yeah.
And what is the last one I need?
Reflexive.
Reflexive. Just A is related to A, right? That's the last one. So anything satisfying, any relation satisfying those three things is called an equivalence relation. Okay? And because it kind of behaves, yep, go ahead.
I just need to freeze right here. I'm wondering about notation. You've got the M. Mm-hmm. Is that like a little sub in front of the B, or are they supposed to be on the same line?
Oh, so this notation was from back here somewhere, right? So in this case, we're looking at this congruence relation, right? So saying A is congruent to B mod M. Another way of writing that, so they don't, because where this mod M can kind of cause confusion sometimes. Right, when I'm thinking about this as an equality-like symbol, right, it's really kind of better to pack that all into that symbol at once.
So it's like a sub on the equivalence.
Yes.
Is that what that is? Okay,
Yep,
perfect.
yep.
That's what I needed to know.
And in fact, probably in my notes, I'll even just write equals instead of equivalent, right? So something like that. Okay. Given an equivalence relation, right? So generally we have a set. Here our set is Z, right? We have a relation, a binary relation, right? What's the relationship between these equivalence relation and some other set theoretic structure? Just involving sets, right? And we've kind of seen, like, if we do, let's say with mod M, let's say this is Z mod M, right? Then I can kind of think of taking my Z and someone said like rolling it up in some sense, right? So I have 0 bar, right? I have 1 bar, and I go all the way. So these are like corresponding to remainders, right? M minus 1 bar, right? And everything of the form N plus MZ is going to be in one of those things, right?
So are you getting to the fundamental arithmetic? Is
No,
that-
not here. No, this is just equivalence classes.
I don't remember
These-
seeing this, Doc. I'm gonna be honest.
These are subsets, right? Of Z.
I understand
right?
what
This
you're
is
saying.
Z.
I'm just saying I don't remember seeing it in the book, so I'm lost on a response.
Okay. Does anyone know?
Are you getting into partitions?
It's a partition, right? So yeah, so I mean, these are all subsets of the set that I'm have my
Crystal,
equivalence
it's
relation
page
on.
17.
Say again?
It's page 17 for Crystal.
Okay.
Thank you.
Yeah, so each one of these are a subset, right? They have the property that they do not overlap, right? So if I take, M, or let's say N not equal to N prime, right? Then N bar here, right? Intersect in N prime bar is going to be the empty set, right? There's nothing in there, right? And in fact, I could say even better. I could say N intersect in bar prime is non-empty if and only if in bar intersect in bar prime, or if and only if they are actually equal, right? Because you're taking the set and you're breaking it up into a partition. A partition just means you're taking a set, you're breaking it up into subsets, right? So that every element of the set ends up in one of the pieces, right? And none of them overlap, right? So you're breaking it into a disjoint union of sets, right? That's what a partition is. Okay. So, like, how could I partition like the numbers A or the letters A, B, C? What are some partitions of A, B, and C?
A, B in one and C in the other.
Yep. So I could have like this. This would be a partition, right? So that would be a partition, right? Another partition would be to put them all in one, right? I could do
Yes.
that. Another partition could be put one in each bit, right?
Yes.
Okay, so there's a lot of these, right?
A by itself and then B and C together. That's the last one.
Yeah, so let's see. Well, no, I guess there could be A and then BC together.
Yeah,
and there
that's
could be
the one I was
B and
saying.
AC together, right?
Yeah.
So there's a few of these things, right? A few of these partitions. Every one of these partitions, okay, this one's just the set, right? These are the partitions done here. Every one of these partitions correspond to an equivalence relation, right? So here's a partition. In this partition, what corresponding equivalence relation would give you classes that have exactly these things? So what would the relation be? Like, is C related to anything? So C is related to something, right? C is related to C, right? Right?
Mhm.
I'm focusing on this one here, right? A is related to A. B is related to B, right? And then also A is related to B. Okay. So as a relation, that relation there involving just those 4 ordered pairs, right, is an equivalence relation on this set ABC, right? Because what is this relation capturing? Well, 2 things are related if and only if they're in the same equivalence class, right? So there's a back and forth, right? You can take an equivalence relation and you can get a partition, right? You can take a partition and you can get an equivalence relation, right? So those are 2 different ways of looking at the same thing. One is looking at it as a relation. One is looking at it as a partition of sets, right? So there's 2 different ways, okay?
Could you say that if and only if statement again, please, Dr. K?
Let's see, how do I want to say it? Yeah, it's a little bit hard. I didn't really put all the, like, I want to say, I mean, this is kind of a vague thing, right? I'm wanting to say, I just want to say there's equivalence relations and partitions are in a one-to-one correspondence, right? So there's, for every partition, you can get an equivalence relation. And the equivalence relation is just A is equivalent to B if and only if A and B are in the same equivalence class, right? Given any equivalence relation, right, I can get a partition. I say A and B are in the same piece of the partition if and only if they're related to each other, right? So we can go either way with those 2 things. Okay. So I mean, if I wanted to get really sort of formal about it, I could say I have a relation R on X cross X, which is an equivalence relation, right? I could define the equivalence relation, the classes X sub R, right? This would be the set of all Y, such that Y is related to X, right? So that would be the equivalence classes for R, right? And I could say, so here I'm starting with an equivalence relation. I'm getting this. The set of these things is a partition. Okay. Now maybe I want to call this partition, it's coming from R, so maybe I write it as P of R, right? Because it's the partition that's coming from R, right? Nothing here is, I mean, I'm just making stuff up sort of as I go here, right? Going the other way, if I have a partition, of X, right, then I can define an equivalence relation, which maybe I will call, and yeah, I'll call it R sub P, right? And so what's going to happen here is I'm going to have A is R sub PB if and only if the equivalence, let's see, if I want to say A and B are in the same equivalence class. So, so what I want to say, there exists a thing in the partition. Let's call it, I'll call it a regular P in my partition, such that A and B are both in P. Right. So again, what is a partition? You know, if you think of X as a blob, right? A partition is kind of like this. Right. So you've got all these non-empty sets that don't overlap and cover all of X, right? So the way I say that A is related to B is I find a block in this thing where A and B are both in there. Right. So that's what it means to say they're related. And then to say that these are essentially equivalent is that the map, if I start with R and I form the partition based on R, right? And then I form the relation based on the partition formed by R, right? Then I get back R, right? So just get back to the same relation. So it's just, you know, given the relation, I can get a partition. Given the partition, I can get a relation.
So this works like the conjugates?
Yeah, it's exactly the same. Yeah. I mean, that's the thing we need to understand as we go forward and we start doing the same sort of thing for groups and rings and fields and other stuff, right? We need to understand all this. Yeah, so in the case where I'm looking, I mean, let's take a real simple case where I'm doing like mod 3 again, right? So I've got this relation, whoops, I got this relation, n is equivalent to 3 to 3. Oh my gosh. M. If and only if, and I can say 3 divides n minus m, right? So that's an equivalence relation, right? The equivalence classes are 0 bar, 1 bar, 2 bar, right? Those are the equivalence classes. This m bar being m plus 3z, all those things that are m plus something that's a multiple of 3. Right, so all those things, right? So this is the partition here. This is the relation here, right? And so from this relation, I get this partition. From this partition, I get that relation, right? So that's the point, right? So it's not a difficult thing. It's just something you got to get your head around once and think about, right? Someone said congruence class. That's something we're not quite talking about yet, but we are sort of because we're doing modular arithmetic. But if you have an equivalence relation where you can also carry over the algebra, right? So here we have an algebraic structure on Z with plus and times. We build this equivalence relation, right? But we can also now define an algebra on the equivalence classes, right? And so the algebra is just like this. It's like m bar plus 3z. Sorry, let's try that again. So m bar plus n bar, right, is going to be m plus n bar, right? Or if I write it with the 3z, it means that m plus 3z plus n plus 3z is going to be m plus n plus 3z, right? So we can carry over that algebra. Same thing with multiplication, right? I can do m bar times n bar is equal to m n bar, right? And if I'm doing my 3z version of this, I'm going to have m plus 3z times n plus 3z is equal to m n plus 3z. Now you don't do some sort of weird algebra with the 3z there, right? So that's important, right? So this is like the plus version and the times version. And this is really part of your homework because in your homework you had this. You had so here's a way of saying it the way it was in your homework. If A equals A prime mod 3, right? And B equals B prime mod 3, right? Then A plus B equals mod 3 A prime plus B prime, right? So that was like one of your homework problems, right? Same thing with multiplication. A times B would equal mod 3 A prime times B prime. All right, so this one there corresponds to that. That one there corresponds to that.
Dr. K, can you wait a second so we can finish writing this down, please?
Mm-hmm.
Thank you.
Yeah, any other questions on this? So, I mean, there's a lot of sort of different ways of interpreting. You're kind of interpreting the same thing in a variety of different ways, right? And the hope is, in the end, we need this kind of set version when we get to rings and groups and all this stuff. But you want to use your intuitions here about the modular arithmetic because they're good intuitions, right? To sort of guide you later on.
Dr. K, I see you are recording this. Do you post our lectures or?
Yeah, I can do that.
Okay.
I mean, I guess I usually do that. You might want to remind me to do it.
Okay.
And
think I
could
did
you
that.
please, yeah, could you please also, because I remember last time you was able to like save this PDF and post it in the announcements. So to go over it all one time, please?
It's kind of too late now because I've been erasing it as we go,
Oh,
right? There was also the problem that I have to switch to black on white, right? If you're going to actually print it, right? If you're just going to look at it, that's okay. But if you're going to print it, then because there was no way to invert those colors after it's made. So I guess if anyone wants me to save it, you should probably remind me when the class starts, right? And if you want to print it, then you should remind me to switch the color scheme right before we start. Okay, anyway, that's equivalence classes, congruence relations. I said I was not going to talk about all this stuff so long, and here I am talking about it for so long. What else? Everyone come up with think for yourself for a second. Let's just take a little tiny break. So think for 3 or 4 minutes of a equivalence relation. Remember, either way, you can think of it as the relation directly, or you can think of it as a set of equivalence classes, right? And then I'll just pick a few of you to say, what is your equivalence relation, right? So let me just sort of set a timer. Let me just do I don't know, 4-minute timer here. And then you can catch up writing and Sorry, that was about 5 minutes. Let me just pick on a couple of you, especially those who have been quiet. So Philip, did you come up with a good equivalence relation, equivalence classes? Is Philip awake? I think Philip might be asleep. Let me try Hugo. Oh no, Philip's awake. Philip, can you hear me? Can you guys hear me?
Yes.
Okay. All right. Hugo, what did you come up with?
Okay, can you hear me?
Yep.
I was thinking similar triangles. Like,
Okay, and so what is the set of things that are going to be in the equivalence relation or equivalence classes?
so it could be like the vertical, what is it called? The vertical distance over the horizontal distance, and then those will all be equivalent to each other in like that ratio will all be equivalent in similar triangles. I mean, I'm not quite sure how to put that in maybe like
do you
a set.
do you mean like similar right triangles?
Yes.
Specifically? Okay.
Yeah.
So
I
okay,
do.
so your set would be the set of all right triangles, right?
Yeah.
And they would be similar if they have this common ratio, right?
Yes.
And so what? Okay, good. All right. So what would so given two of these triangles, right? I'm going to associate two of them with a ratio, with a number, right?
Yes.
Okay. So we could also think about this as a mapping. So this is kind of fun, right? Because we could map like an arbitrary triangle. And I guess in some sense, yeah. So I mean, this is sort of fun because geometry is always like, let's say these two were actually exactly the same. And let's say, I don't know, this is let's say 3 and 3, right? So are those actually the same triangle or are they similar triangles?
Those are, I would say, the same.
So these are the same, right? So we're not like locating them in space or something. There's like, this is the Platonic triangle that's got this shape, right? So this will be similar to one that looks like 1 and 1, right? So all those will be similar, right? Okay, and then we could, right, have this kind of function going from right triangles to what? To the reals, actually, right? Or maybe the positive reals.
Yes.
I guess really like numbers bigger than 0 all the way to infinity, right? Like that, right? And so every triangle, so and what it's going to do is it's just going to output this ratio, right? Let's say, yeah, I guess, is it clear which one is up and down? Like, how about this? Ah, yeah, no, this is good. So are these, oops, sorry, let's do it like this, right? Let's say this was 2 and 3. Are those two the same?
No, those would not be the same.
So how would you, like, okay, so what if I started rotating this one around? See what I'm getting at? Like,
yeah.
When do they become the same, right?
Mm-hmm.
So I'm thinking maybe in a ratio we would define like the smaller side over the bigger side, right? for the ratio,
Okay.
just to be specific, right? So that actually this is going so we don't get all the way to 0, but we get to 1, right? Like that for our ratio. Right, and so every triangle we would define like the smaller side over the larger side. We would actually use up every possible number in there, right? And the equivalence classes would be those things, right? So this is a nice example of a way to build an equivalence class. So if I'm given a function, so here my function is right triangles, right? And over here my range is this interval. Right, and taking some collection of these right triangles here and mapping them to whatever value it's got there, right? So like that. And then you look at all those that map to the same place, right? So I take this particular value, let's say this is like a quarter or something, right? And I pull that back and I look at all those things that map to a quarter, right? That's a very natural way of making an equivalence class, right? So anytime I have a function going from X to Y, right? And I look at the pre-images of things in the range, right? So I can say X is equivalent to X prime if and only if f of X is equal to f of X prime. Right? So those things that get mapped to the same place, right? So that's kind of what's happening here. We're taking these triangles and mapping them to a number between 0 and 1, right? So that's a nice way. Yeah, that's a nice equivalence relation, and it's nice and kind of abstract because like where are the platonic triangles out there, right? I mean, you could keep. Anyone else have one they want to share that you came up with?
I shared one in the chat, Doc. I think that has to do with the equivalence from using the modular and creating the remainder, but I'm not sure, so that's why I uploaded it to see if, I don't know if you're able to click on it or not.
I think it's coming up. Yeah, I mean, yeah, but this is the example I've been talking about the whole time, right?
Yeah, but you were using 3. I use modular 4.
Yeah, well, I mean, okay, yeah. So I mean, modular m, right? For any m, right, is sort of but yeah, this is a good example, right? I mean, this is our sort of canonical example so far, right? So yeah, I mean, if we take any m greater than 2, right, then we can build 0 through m minus 1 bar, right? That would be like the equivalence classes, right? And then you would have A is equivalent. Yeah, okay, so A is equivalent to B mod M, right? If and only if M divides A minus B, right? And the algebra is exactly like you said there, right? So it'll be like, if I want to add two things together, A MZ, plus B like MZ, right? Would be, oh, sorry, that's a multiplication, so I'll do multiplication, be A, B, right, plus MZ, right? So yeah, I mean, this even has all the extra algebraic structure on top of it, right? So lots of good structure.
Dr. K, is what Hugo brought up, that's the clay things with the rotations and the flips. And from my research, that's not modular arithmetic. It's similar, but it's not the same.
No, we're not, yeah, but I'm not talking about modular arithmetic here. I'm just talking about equivalence relations.
So when you use the triangles, I got lost is what I'm saying.
Because he gave an example of an equivalence relation on triangles, right? And also we have the equivalence classes. This is a very general notion. Equivalence classes, right, would be all the triangles that are equivalent in this sense, right? So that would be the equivalence classes, right? I mean, it could be something simple like I've got a group of students and everyone who's wearing blue, right, is in one class, and I mean, it's a very, very general notion, right?
Okay, I get it now. I understand. But there's no specific traits or characteristics that we're looking for other than this is what we're defining it as.
Yeah, I mean, we're just talking about equivalence relations and equivalence classes, like the relationship between partitions and equivalence relations.
Okay.
Right, in general, right? So that's sort of what I'm wanting to get at. Anyone else come up with one that was interesting?
I had a thought, and I'm not sure exactly how to position it, but could it be could equivalence relation be like a quadratic equation with, say, 2 as the square coefficient and 3 as the linear coefficient? Would that be
So like
equivalence relation?
2x squared plus
3x
bx. Oh, sorry, like 3x
plus anything.
plus c,
Or c.
right? So
Yeah.
so all the things like that, right? So we'd say here's an equation. These would be equivalent. So we're going to look at just quadratic. Let's call it Q, right? Just quadratic equations, right? And we'll just
Yep.
define. Let's see, and I'm going to define 2 are equivalent if, yeah, how would you define the equivalence there? If they have the same C, so maybe this isn't all quadratic equations. These are all the ones that look like 2x squared plus 3x plus something.
Plus something, yes.
Plus something, right? So it's not really all quadratics. It's just this part plus something, right? Yeah. Yep. So that would be an equivalence relation. What would be, or maybe the equivalence classes? How many things are in each equivalence class?
So I think like completing what Allison just said, like if we have, let's say, an order pair 2 and 3, so if like related to the quadratic, if a plus b equal to 5 and a times b equal to 6, so we can use it as a roots of this quadratics. Is that work in this case?
I mean, just what are you defining to be the, I mean, I think Tringle's example was just this. So we're basically mapping this thing to C, right? That's kind of the map. If I were going to do it like a mapping way, right? We're just taking this 2x squared plus 3x plus C, right? And we're mapping it to C. We're sort of looking at that as the thing, right? Dina, I'm not sure, were you saying something different, I think? You're like looking at the roots or something.
Yeah, because I thought about this way also, if I can just show an example, like using an order pair and using the same concept related to the quadratic. So it's just like kind of same idea, but like Tringle like posted in a little bit different. So I'm very interested if it's same as my thoughts or different.
So yours is like this, right? You're looking at x minus a times x minus b.
Yes, yes. So if I
doing
have
something like that.
Yes.
And what is your relation?
So if like a times b and a plus b, this could be the roots of the quadratics. And can I substitute it in the quadratics and try to go over the proof to like show that they are equivalent to the roots?
So yeah, and so what would you do? I mean, yeah, these are good thought experiments, right? So let me keep that one. I think it's a little different but similar, right? And I think in some sense, okay, so let's think about the first one, because I think it's a little bit different. So in the first one, every C is going to correspond to exactly one of these things, if I interpreted it correct, right? So there's really no grouping here, right? Like something is related to just itself, right? Like 2x squared plus 3x plus 5 is not related to 2x squared plus 3x plus 4, right? Because we're just everything's dependent on this C. Right, it's sort of where everything is depending on, right? So what this is doing is sort of looking at some particular quadratic. I don't know, just draw it like this, maybe, right? And then say the axis. I don't know where it is, right? Say the axis is there, right? And so you're just sort of moving this up and down by a constant, right? Something like that, and you're saying that 2 are equivalent to each other if and only if they are actually exactly the same, right? So I think, right, if I'm understanding this one correctly, kind of the equivalence relation here is just literally being the same. So there's only one thing in each equivalence class, I think, right? Now, with this idea of moving things up and down, what does that sort of remind you of? It's, if you teach calculus, for example.
Vertical shift.
Well, so it's a vertical shift, but you might be looking at all the things with the same derivative,
Mm-hmm.
right?
Yeah.
Because all you're doing is moving things up and down like that, right? And then like this
Oh,
one,
Fields families, yeah.
yeah, so then everything in this family would be equivalent to each other. Everything there would be equivalent to each other, right? So that's a little bit different, right?
Does that make it a equivalence if we're talking about it at the calculus level?
Well, yeah, I mean, we could think about that, right? I mean, we could just think more generally. Let's take functions, say from reals to reals. You know,
Mhm.
let's say they're total functions on all the reals, right? And I could define an equivalence relation. F prime is equivalent to G prime. Sorry, take that back. F is equivalent to G, if and only if F prime is equivalent to G prime.
Didn't work.
Right? Sorry, if and only if F prime is equal to G prime, right? So that would work fine, right? Because I'm saying, I mean, basically we can do it with the function idea. I'm going to take F and map it to its derivative, right? I'm going to take G and map it to its derivative. And if they're the same, I call them equivalent, right? So that would definitely be an equivalence relation. What if I tried the other way around? Suppose I took F and tried to map it to its indefinite integral. I mean, that's actually kind of vague, right? Because like, what do you do with this extra C out here, right? So you'd have to be careful about what you mean by doing it in that direction. The other one here, this one, right? So geometrically, what's a way of thinking of this kind of equivalence relation? I mean, like what would the things that are equivalent here be?
All the things whose product equals 0.
Well, so I mean, maybe if I threw in an extra, I don't know, something like this, like a quadratic. In fact, let me not even say like this. Let me do what you said and say, let's take f of x. So this is just a quadratic, right? And where it just has the property that f of a equals f of b equals 0, right? So it has those two roots, right? Then any quadratic going through those 2 points, right, would be equivalent to each other, right? And there's probably a few, right? It's probably an interesting collection. Like I could scoot the right, given any 3 points, I can find a quadratic through those 3 points, right? So actually, given any points in here, I could find a quadratic, right? I couldn't find one. I gotta be careful. Anyway, we're getting a little bit sidetracked, right? But anyway, yeah, these are good examples, right? All sort of fun examples. I think it's kind of fun to think, you know, you wanted to try to prove that it is an equivalence relation. Try to do it by sort of by picture in some sense, right? What would the class of things that are equivalent to each other be? It would be all those quadratics that are going through those 2 points, right? And then I guess you'd have to think, does it include that one, right? Maybe it includes that one. That kind of, where did Dina, did we lose? Oh no, there she is. Does that kind of click with what you were thinking, Dina?
Yes. So
Okay.
I thought if we have like the roots at this case, and so the similarity, if we have many like parabolas going to the same thing, and also like because one of the quadratic formula, let's say I have order pair 2 and 3, and I need to like kind of prove it through the quadratic. So the same way that you started the proving like a plus b, like we take in 2 plus 3 equal to 5 and a times b equal to 6. So we're using the same two numbers or for the order pairs. and now I plug them in the quadratic. So in the middle, it will be like x squared minus x times a plus b plus a times b, and I try to go from there. It's kind of also showing similarity. And at the end, when we solve this quadratic, so the roots will be also 2 and 3. I'm not sure if this is the right way, but yeah.
Oh, I see. Someone gave me a picture here too. Yeah. I'm not sure. So do you mind like sending it to me and let me think?
So do you think I can just write it in a piece of paper and share it now?
Yeah, you can. Yeah.
Okay.
I'm losing track of what you're saying a little bit.
Okay.
So Doc, I did a quick screenshot and made see a slider with Desmos to show the image of what Tringle was describing. And I think that's what we were discussing, is that the parabolas, they still have the same speed no matter what. They're just translating up and down.
Yeah,
So
that's the sort of image I had in mind. But it's actually a little bit different than what she said, but this was sort of a nice other example that's similar, right? All of these parabolas would have the same derivative, right? That's kind of the thing. Yep. And that's a good example. I mean, there's an example of equivalence classes you use in calculus. You don't think about it much, right? But that's an example of equivalence. That's sort of what that plus C is when you're adding the plus C when you're doing indefinite integration, right? You're sort of looking at that and saying, all these things have the same derivative, right? So you're sort of encapsulating that with that plus C that you're throwing on there, right? That's a kind of equivalence class thing.
Dr. K.
Yep.
I think Dina was talking like a set of quadratic equations that have the same roots, I think is what she was getting at. But I'm not sure if that's that's what I understood when she was explaining it.
Yes, I tried to. Yes.
That was the picture I had, right? So it's like we have these two roots, right? And then we're just looking at all the quadratics that go through those two roots, right? So they would be fixed, right? We have all the quadratics that go through those two roots. But like, what would all those quadratics be? They'd all have this aspect to them, right? And then what's the other thing that they have? They would have some constant here, right? I think this is the only thing you can have, right?
Well, with that one, Doc, wouldn't the speed change consistently if the sliders can change? That would change the speed of the with C being a coefficient that changes. I don't know.
Yeah, that'll change the slope for sure. Yeah.
Definitely.
Yeah. So here we're just pinning it to all the different quadratics that can be drawn through those two roots, right?
Yes.
Okay, but I believe it's true that if I give you any three distinct points, you can always make a quadratic going through those three distinct points, right?
Yes.
So if I pick any point at all that's not A or B, then I've got a corresponding quadratic going through those 3 points there, right? So all of those, so it's like this pair of roots is what's pinning down the equivalence classes, right? This pair of roots. So all the things that have this pair of roots, right? So given a different A and B, you would have a different equivalence class, right? So the equivalence classes would be those things with these roots, right? Now there's a bunch of them. I can put any constant there I want, right? So all those things are in the equivalence class. Good. Okay, but I think we get the idea, right? Equivalence classes are very general sort of thing. With the algebraic structure, we get more. We're able to extend the plus and times to the equivalence classes, right? So that's an even, so there we're going from an equivalence class to a congruence relation, right? Congruence relation, again, doesn't just mean modular arithmetic. It's congruence in any sense. So we're going to do this with groups and rings and all sorts of things as we go, right? There'll be lots of congruence relations.
I don't know about that.
Let's see. Okay, so let's go into groups because I'm never going to get there if I don't. So there's a bunch of good number theory. How to compute whether or not two numbers are relatively prime is important. Bezo's result, how to So, I mean, this is a result. Let me just mention it because it comes up a lot in the class. Given numbers A and B, right, with GCD of A and B equal to D, okay. So this means that D divides, so this means D divides A, D divides B, right? So D is a divisor of both of those, right? And moreover, if, what's it mean to be the largest divisor? If D prime divides A and D prime divides B, what's my relationship between D and D prime?
They're the same.
They don't have to be the same, but if I have, so this D is supposed to be the greatest common divisor, right? Here's something which is a common divisor. So what property does D prime have to have with respect to D?
It has to be divisible by D.
The other way around, right? D prime has to divide D, because D's the biggest, right?
Okay, yeah.
Right. So yeah, so that's what it means to be the biggest, the greatest common divisor, right? And so what Bezo's theorem tells you is you can always find a solution, in fact, infinitely many solutions to AS plus BT equals D. Okay. Now, those of you who did this on your homework in the DQs, right? Everyone who did this, I think, did it correctly, but you did it in a way that would be hard to generalize to very large numbers, right? So there is a very nice algorithm for coming up with this S&T, which you might want to look at some. Okay, it's exactly what you were doing. You're sort of doing it by hand and sort of working backwards you're working backwards from taking the modulus over and over, right? You're sort of repeatedly taking the modulus, right? But there's a very nice way. So, I mean, we're just going to run out of time. So let me not dwell on this too much. We will do examples of this. And I think I gave you here a link. Yeah, I give you a link to an Excel sheet that actually does this calculation. So you can sort of look at that. I discuss it in the video quite a bit. I'm going to go on to groups before we just totally run out of time. What are the axioms of a group? So what are some examples of groups? Let's start there. Like, is this a group? We've been talking about Z a lot. So we have Z, we have 0 and 1, and we have plus and times. Is that a group?
Yeah, and then we have like
Yes.
Q rational numbers.
So this is not a group as it's written, right? This is actually what we're going to call later on a ring. So inside of this ring, do we have something that is a group?
The integers over addition where the identity is 0.
0 and 1, and plus, right? So this is a group. Why is this not a group?
Is it because the inverse of the inverse is not necessarily an integer?
Yeah, and in fact, there's only two things that have inverses here. And those things that have inverses are called units. What are the two units here? So 1 is one of them, because 1 is its own inverse. There is one more. What is the other one?
0?
So 0 is not, because you need to multiply to get 1, right? To be multiplicative, to be a multiplicative, the inverse is determined by what the identity is. I mean, that's a good point, right? So over here in the additive part, 0 is the additive identity, right? So to be the additive inverse means that you're something that adds to something, right? So A and B are additive inverses if A plus B is equal to the additive identity, right?
Mm-hmm.
A and B are multiplicative inverses if A times B
equals 1.
1, the multiplicative identity, right? So once you have an identity, you can talk about inverses, right? Okay, so the only things that have inverses here, so 1 obviously has an inverse because 1 times 1 is 1. What's the only other thing that has an inverse here?
-1?
-1, right? -1 times -1 is 1, right? So like -1 inverse is -1, right? Okay. What if we went to like Zi? What are the units there? So 1 and -1 are still units, right?
I and negative I?
So I and negative I are multiplicative inverses, right? Because this is equal to 1. Right? Good. Okay. Let's go to a harder one. Let's take Z6. Right? So what are the elements of Z6? There's 0, 1, 2, 3, 4, and 5. This is a multiplicative, sorry, this is an additive group, right? Because we've been talking about that. Right? So I can take these things and like 1 plus 2, think about these as being the bars, right? This is 3 bar, right? Let's say 4 plus 5. What does that equal in this thing?
9.
So it's 9.
So
it's the same
3.
as
2. No.
Same as 3, which is the
3.
same as 0, right?
Yes.
So it's actually the same as 0, right? So 4 is equal to -5 here, right?
Why is it the same as 0?
Because 9 is divisible by 3, right? So 0 bar is equal to 3 bar is equal to 9 bar, right? Anything divisible by 3, right?
But it's Z6 though, boss.
Oh, I'm sorry, Z6. No. Yeah, sorry, my bad. So, yeah, so you were right. So it's 3, right? Sorry.
Alpha.
Yep, I was going crazy there. So this is 3 bar, right? What? Okay, good. Okay, what is the additive inverse in Z6 of 4?
Two,
right? Because 4 plus 2 is 6, right? So you get 0 bar, right? So that's like the in general in ZM, and let's say we have an N, like N in ZM. What is the additive inverse of N?
M minus N.
It's M minus N. Good. Right. That's good to remember, right? I mean, this will come up a lot. Okay. What about on the multiplicative side? So is Z6, so let's throw away 0 because we know we can't have 0 in there, right? So let's just take 1, 2, 3, 4, 5. Is that a multiplic? So this is something we'll call Z, I don't know, star is when I drop the 0. So now I can multiply. Is that a multiplicative group?
Are you asking about the full 1, 2, 3, 4, 5?
Yeah.
I don't see how. Well, it depends, but a multiplicative group, if it goes
all the
into
remainders belong in the set.
Yeah. So we know that if we multiply, we have a good notion of multiplication, right? So like 3
Right.
bar times 4 bar. So this is going to be 12, right? This will be 0 bar,
Mm-hmm.
right? So actually, this is already a problem, right? I mean, because I took 2 things in there and multiplied them together and got 0, right? So that's already a problem. So maybe I should have just asked, is this a multiplicative group? Like, is there a problem
still
with?
Yes.
No, I mean, but the answer was no here, right? If I throw away the 0,
Right. But
and the
now it
answer's-
is.
Well, is it? So I still have this, right? If in a group, can I have something
Because
like
the
this?
0 is not in the set, so no, it's still not.
Well, now the
because you have
0's in there. So let's look where we put the 0 back in, right? So now I don't have to worry about closure. I know that I can multiply and stay inside of Z6, right? But is it a group? What bit of being a group fails?
I thought it had to be listed in the set, boss.
It is. If I multiply any two of these things, I stay inside the set. Remember, these are
Okay,
But you don't have 0 listed.
but
that's fine.
okay.
Okay, fine. I'll put 0 in there. There.
Okay, thank you.
Yeah.
That was driving me
You-
crazy.
Okay. Is
Okay.
that a multiplicative group?
Yes.
Like, does this cause problems with this being a group? So what problem does this cause?
You can't divide by 0.
Ah,
You can't divide by 0. That's a real problem, right? There is no 0 inverse. That's a real problem. It's also the case that can 3 have an inverse, given that 3 times 4 is equal to 0?
No.
Yeah, right. I see some head shaking, right? If 3 had an inverse, I would be able to do some algebra on this, right? And so this would be 1 times 4, right? This would just be 4, right? But this is equal to 0, right? So this is 3. Sorry, let's back this up. This is 3 bar inverse times 0, right? Which is 0, right? So 4 would be 0, right? So that would be a problem, right? So if I have any two things that multiply together to give me 0, right, where the two things themselves were not 0, then I can't be a group, right?
Okay,
It's like-
Dr. K,
Yep.
before we move on, can we just go back? Okay,
Mhm.
earlier you said that you had like a little star above the 6. I think like a little asterisk above the Z, trying to say like it was Z6, Z asterisk, then the 6 right there. Did you state that right? Okay, what did you say that mean right there? You said that mean like the 0 is not listed. The
Yeah,
0 is not
so
listed in the set.
So in general, when I have a ring, so it's something with a plus and times and 0 and 1, and I put a star there, I'm going to mean that I take the ring and I take away 0.
Okay, thank you. That's what I was
That's
trying
in
to
general what that's going to mean.
And that question,
Um,
and you stated that the question was going back up to that problem, the problem right here that you listed right here. You asked,
Mhm.
was it a group? You asked, was it a group? Well, that's the question you said, was it a group? We had said the answer was going to be no, right? Because the 0 was not listed. That's what I hear. Did I hear that?
So in that case, right? So this thing right here is not a group. So there's various reasons things are not a group. So here it's not a group because it's not closed under the operation of multiplication, right? I can do 3 times 4 and I get 0, and 0 is not in there, right? So to be a group, it would have to be when I take two things and multiply them, it's got to stay in there, right? So that's one of the parts of being a group. So that's a different reason than the reason Z6, where now we have everything. So I wrote 6 here, I mean to 5, right? Okay, now this is not a group because, well, one reason is because 0 doesn't have an inverse. Everything has to have an inverse, right? So it's not a multiplicative group, it's an additive group, right? Is there a multiplicative subgroup of this? So what's a subgroup? Is there a subset of this which is a group, multiplicative group? So it would have to have 1, right?
Would it just be 1, 2, and 3?
So let's sort of play with it some. So is 1, 2, and 3, would that be a multiplicative? So this is like I'll just use some notation. Let's say we're taking a subset here, right? So H is that, right? Is this a multiplicative subgroup? So does 2 have an inverse?
Wouldn't it be 3?
No, multiplicative, right? So we're thinking about the multiplicative part.
So wouldn't
so
it be
2
no, because 3 would end up at 0 again, which isn't in the group?
2 times 3 would still be 0, right? So yeah, that's still a problem, right? So that doesn't work, right? This is a multiplicative subgroup all by itself, right? If I just take the multiplicative identity, that's a multiplicative subgroup, right? So this is a trivial subgroup. That's always going to be the case. There's one more here. Can you see one more? There's
Can I
something
do one
else.
and three?
Yep. Huh? So it's
One
got to have
and three.
one. So 1
Mhm.
and 3, is that going to work? So what's 3 times 3?
Oh, that's 9, not 3. Well, 9.
9, so that
Is
gives me
3.
back to 3, so that's cool, right? But do I have a way of getting, do I have a multiplicative so it is closed under multiplication now, right? But do I have a multiplicative inverse there? The only options are 3 times 3 and 3 times 1, right? And neither of them are giving you 1, right? Now, is there another option? So 3 doesn't
Would 1
work.
and 2 work?
Would 2 work? Is that what you're saying? Would 2
Yeah,
work?
1 and 2.
So if we tried 1 and 2, right? So does it work? So what's 2 times 2?
4.
4. So we
Take
we
out
need to
3,
have it.
1.
Yes. So we need to have at least 4 in there. Now what's 4 times 2?
8.
Which is the same as?
Oh,
Same as 2, right? So that's not quite working. So is there another option? So so this one doesn't quite work. All right.
I'm thinking just gonna be 1, huh? That's the only option we have.
So that's always going to be 1, right?
Is that
But
always
there's
gonna be
actually one
1?
more. What happens with 5? What is 5 times 5?
25. Oh, and you get back to 1. So
You get back to 1, right?
yeah,
Yep. So there is a multiplicative subgroup there, 1 and 5, right? And this gets to that Bezo's theorem that I was talking about before, right? So what's going on here is that GCD of 1 and 6, remember we're modding out by 6, right? Is 1, right? GCD of 1 and 5, of 5 and 6 is 1, right? Those are relatively prime, right? 1 and 5 are the only things that are relatively prime there, right? Now, suppose I'm working in ZM, right? And I've got N, which is relatively prime. Some of you did this for your DQ. Right? When it's relatively prime like that, what happens? I can write this as NS plus MT equals 1, right? That's what the Bezo's theorem tells us. Right? And what does this tell me? So M, we're in ZM, right? What does this tell me about N? Like what happens when I take this whole sort of equation and do mod M? What happens to the
Does N
MT?
has to be prime?
N doesn't have to be prime. I mean, the primes do come in here, but it doesn't have to be prime. But when I mod out by M, what happens to M times T? What does it become?
just T.
No, what does M become when I mod out by M?
0.
Like it becomes 0, right? So this just becomes 0, right?
Like that.
And so this becomes
Why?
NS equals 1 mod M, right?
Why?
Why? Because that's all that's right. That's what's left over, right?
Oh, my mic
mean-
is open. My bad.
Okay, sorry. Right, and so what is this? So if this GCD is 1, then I get this. And what does this tell me about N? What does it tell me about N and S?
They're inverses of each other.
They're inverses. Tringle, I see your mouth talking all the time, but your mic isn't on. So I don't know if you're wanting us to hear you. right? They're inverses, right? So S is equal to N inverse NZM, right? So what we have here is we have that NZM has an inverse if and only if the GCD of N and M is 1. Now, some of you did this for your DQ, right? And I looked at a couple of you who did that one. Right? So the things that have inverses are going to be those things which are relatively prime to M, right? So let's take another quick example, and then we'll have to stop. But let's take Z12. 1 is always relatively prime to anything, right? Is 2 relatively prime to 12? Come on, everyone, give me an answer like that. Does 2 and 12 have a common divisor?
2.
Yes,
2.
2.
They have a common.
Is 3 relatively prime to 12?
No.
No.
4?
No.
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 5? How about
Yes.
5?
Yes.
And then 5's prime, so of course it is, right? 6, no, right?
No.
7's prime, so
Yes.
it is, right? And then on through 11, right? 11 is prime, right? So these are actually prime, so they're definitely relatively prime to 12. Does this form a multiplicative group? So this set of things in the book is called U12, the set of things which are relatively prime, right? The fact that each of these are relatively prime to 12 means they have an inverse mod 12. That's what we have here. And that's coming from Bezo's theorem, right? That's where that's coming from.
Okay. That makes sense.
Okay. And so what, yeah, so like I do 7 times 5, what is that?
35. And then
35 and mod 12. So it's
11.
like
that would be
It's a-
11. Remainder
11, yeah. So my way of thinking of it is -1 mod 12 in a way, right? But yeah,
Yeah.
11, right? So that's 11. What's 7 times 7?
49.
And mod 12
That's what.
is 1, right?
It's
49,
one.
right?
It's 1.
And what about 5 times 5?
25.
25.
Which is
One.
1,
One.
right? And what else do we have here? I guess that's all we have, right? And then of course
11
5 times 1.
11.
Oh, 11 times 11. Yeah, what's 11 times 11?
121.
Which is
1.
1, right?
Mhm.
So which elements in here have square roots, right? That's an interesting thing.
Square root.
Which things have square roots?
The 7, 5, and
1.
11.
1 is the only thing you can take the square root of.
I
You
think
can't
1
take
is the
square
only
root.
thing here that has a square root, right? Which things are perfect squares?
1.
So 1,
Oh,
right? It's a
One.
perfect square, right? Wait, what am I? Let's see. Hold on just a second. Yeah, sorry. What are the square roots of 1? I'm getting there sooner or
You're
later.
getting jokes. 1.
Yeah, so square root of 1 is 1, but it's also 7, right? It's also 5 and it's 11. Every single thing in there is a square root of 1, right?
That's pretty. That's very pretty.
And 11 is actually -1 here, right? So right, so the square root of -1, right, is also in there, right? So that's anyway, it's kind of, yeah, it's kind of fun to think about these things, right? So this gives you an insight into some things become kind of fun and different here playing with these. All right. Anyway, so much for trying to get through this quick. Any last minute questions, and then I'll be happy to post this. And if you want me to save the notes next time, even though they're kind of a mess, especially if you want me to print them, remind me before we get started.
I have a quick question. Where do we access those mini lectures with those videos? Because I haven't been able to find them.
Oh, okay. Let's go to the main class page. So the link I gave you for the class, right, there is a lot of stuff here. Oops, that's the wrong class. Let me go back. So the main class page is this, right? So this is, oh, sorry, you're not seeing this. Here you go. Right. So this is the main class page, right? So this is what you should see. And there's a bunch of videos, right? There's too much here. I mean, you would want to pick and choose what you watch, right? But then here's this mini lecture. That's the one I was just looking at. Right.
Okay, thank you.
And there's some sort of facts and summary. These are like little sort of quick summaries and facts. This thing is AI generated, and it's got kind of this fun podcast-like thing that's attached to it. So that's sort of interesting to listen to. Then I have some of those videos up there. I have some suggested ones you might look at here. The AI tutor is there if you want to try that out, and then yeah, all that stuff. Anyway, it should all be here, right? So I try to keep everything in this one page.
I missed that little link for the mini lecture, so thank you.
Okay, good. Yeah, there's a lot of videos in there. So I've got all the mini lectures have videos. So, and in fact, that one link here, the one you've been looking at, it actually has the first 3 topics, right? So it's got topic 1, all the videos for that, topic 2, and topic 3, right? So there's a lot of stuff here to look at.
Thank you.
Good. All right. Nice seeing everybody again. Sorry, I forgot that I'd seen you all before.
I have a question.
Yep, go ahead. Yeah, anyone who wants to leave
Dr.
can
K,
leave.
there's
Anyone who
no
wants
way
to
you
stay.
forgot me. Nobody forgets me.
I did not forget you, no.
Thank you. Good night, everyone.
Anyone who wants to stay and ask some last minute questions can just stay. And you can ask. Go ahead and ask. Yeah.
The reading quizzes that are on like the weekly readings and stuff, how do you grade those? Because I submitted my reading quiz, but then I saw that there was an option to go back and change answers after it's already been graded.
So it's really just a participation. So if you've done it, you've done it, right? I mean,
Okay.
do your best, but that's sort of like it's a 1-0 thing. You either did it or you didn't do it. That's
okay.
So yeah.
And those are due Sundays, correct?
That's what I'm saying, because I'd like to sort of look and see how you did. So I did look and see how everybody did. And so everything was pretty good. I mean, everything I've seen so far looks pretty good. Those look good. The DQs so far look pretty good. So what I'm saying looks pretty good so far.
Okay, thank you.
Yep. Anything else?
So I have a question about when homework's going to be posted. So have the new homework assignments been posted for next week as well, or when would that be posted? Like you're gonna do that like on a Wednesday or Thursday?
I mean, I
Like
could
going-
just post it. Do you want it now?
No, I don't want it now because I'm way behind. I'm still on chapter 2, but I'm just trying to. I need to get a schedule going because I'm just this. Oh my God, just working full time, and I was doing well when we was out work, but now that I'm started back school,
yep,
it's sort of kind of it's time consuming. It really is. I was parents emailing me and calling me the type of work I'm not a teacher, and this LaDonna, I'm not a teacher per se, but I help students get on track. To get their credits, to gain their credits back. So they sit there and do their work online, but at the same time, I have to submit documentation to the counselors so they can actually graduate, in December. Yeah. And so they closing out classes like daily. So I'm like so far behind in work while I get my paycheck. And then I'm also trying to keep up with the class as well. So that's why I was just asking, especially when the homework is due on Wednesday. So I was just trying to see when is the earliest. With the homework be posted, because I'm trying to get like a routine going.
I mean, I could post it tonight. I was just going to give you 1 week at a time. So
yeah, that's fine. Do 1 week is fine. I'm gonna figure out whatever routine you stick with, whatever routine you have. That's what I'm gonna go with. I'm just trying to stick with that. I'm just trying to see what's your days when you want your work. I think Sunday and go ahead.
Yeah, I think your class started on Wednesday, so I would post it either late Tuesday or early Wednesday.
Okay.
I think that would be sort of the schedule. Yeah.
And Saturday be DQ1 homework, and then DQ1 assignment be due on Saturdays,
I think that's right. That sounds right.
and something else is on Sunday.
I think Sunday DQ2 is due. Is that right? Or is it today?
I think
Actually, I don't
it's due
remember.
today. I think it's due today.
Okay. Okay.
Today. Okay then. All right then. Thank you. I'm just trying to keep up there on Wednesday.
Yeah, sure.
Okay. Thank you.
Mhm. Did you guys have some questions? Nope, you're just hanging out. So I close the screen. Okay. See you guys.